there! Let's talk about chemistry. It might sound like a big, scary subject with strange symbols and long words, but it's really not. Chemistry is simply the science of stuff. It's the study of what everything is made of, how it behaves, and how it can change from one thing into another. Think about it. Everything you can touch, see, or smell is made of chemicals. Your phone, your lunch, the air you breathe, and even you. It's all chemistry in action. It's the ultimate guide to understanding the world at its most basic level, from the tiniest speck of dust to the biggest star in the galaxy. So why should you care about chemistry? Well, because it's happening all around you all the time. When you cook an egg, you are doing chemistry. The heat changes the runny, clear egg white into a solid white form. When you use soap to wash your hands, chemistry helps lift the dirt and germs away. Even a simple act like breathing is a chemical process. Your body takes in oxygen from the air and uses it to create energy, then breathes out carbon dioxide. Understanding chemistry helps you understand how the world works, and that's a pretty cool superpower to have. Chemistry is like the master instruction manual for the universe. It tells us why sugar dissolves in water but sand doesn't. It explains why a metal nail rusts when left out in the rain, and why baking soda makes a cake rise and become fluffy. Without chemistry, we wouldn't have plastics, medicines, batteries, or colorful fireworks. It's the science that connects physics, the study of energy and forces, with biology, which is the study of living things. It's the bridge that explains how non-living materials come together to create life and everything that supports it. It's the secret code behind reality itself. Getting to know chemistry is like becoming a detective. You learn to look at ordinary things and see the extraordinary secrets they hold. You start asking questions like, what makes that happen? Or what is this really made of? And the best part is, chemistry has the answers. This guide will help you start your journey. We'll meet the tiny particles that build everything, see how they hang out together, and discover the amazing transformations they can go through. Get ready to explore the incredible world of chemistry, the science that makes everything, well, everything. Let's start with the smallest and most important character in our story, the atom. Imagine you have a giant Lego castle. You can break it down into smaller walls, then into individual Lego bricks. But what if you could break the brick itself down even further? If you kept breaking matter down into its smallest possible piece, you would eventually end up with an atom. Atoms are the super tiny building blocks of all matter. They are so small that millions of them could fit on the head of a pin. Everything in the universe, from your own body to distant planets, is made of these amazing little particles. Even though atoms are tiny, they are not the end of the story. They are made of even smaller parts. Think of an atom as a mini solar system. In the center is the nucleus, which is like the sun. The nucleus is packed with two types of particles, protons, which have a positive charge, and neutrons, which have no charge at all. They just hang out and add some weight. Whizzing around the nucleus like planets are the electrons. Electrons are super lightweight and have a negative charge. They move so fast that they create a blurry cloud around the nucleus. The number of protons in an atom's nucleus is what makes it unique. It's like its personal identification number. For example, any atom with just one proton is always a hydrogen atom. An atom with 8 protons is always an oxygen atom. The positive charge of the protons pulls on the negative charge of the electrons, keeping them from flying away. In a normal balanced atom, the number of electrons is the same as the number of protons. This makes the atom neutral with no overall charge, because the positive and negative charges cancel each other out perfectly. So the atom is the fundamental unit of everything. It's a busy little bundle of energy with a heavy positive center and a cloud of zippy negative electrons. These atoms are the characters that make up the entire cast of chemistry. They are the reason why a diamond is hard and a balloon full of helium is light. Their structure and how they interact with each other is the key to understanding all the properties of matter. They are the true superstars of the chemical world, the foundation upon which everything else is built. Now that we've met the atom, let's talk about the elements. An element is a substance that is made up of only one type of atom. Think of them as the purest gangs in the universe. For example, a block of pure gold is made up of nothing but gold atoms, all with 79 protons in their nucleus. A balloon filled with helium is made up of only helium atoms, each with exactly 2 protons. You can't break an element down into a simpler substance by chemical means. It's as pure as it gets. These are the fundamental ingredients that chemistry uses to cook up everything else. There are over 100 known elements, and each one has its own unique personality and properties. Some elements are metals, like iron, which is strong and magnetic, or copper, which is great at conducting electricity. Others are nonmetals, like oxygen, which is a gas we need to breathe, or carbon, which is the basis of all life on Earth. A few are in a special group called metalloids, which have properties somewhere in between metals and nonmetals. Each element is like a unique character with its own story and role to play in the world. Scientists give each element a 1 or 2 letter symbol as a shorthand. It makes writing down chemical recipes, called formulas, much easier. For example, O stands for oxygen, H stands for hydrogen, and C stands for carbon. Some symbols come from their names in other languages, like Latin. That's why gold is Au, from aurum, and iron is Fe, from ferrum. These symbols are the alphabet of chemistry. By learning them, you can start to read the language that describes what everything is made of, from a simple glass of water, H2O, to a complex sugar molecule. So, the elements are the basic chemical substances from which all other things are made. About 90 of these elements occur naturally on Earth, while the rest have been created by scientists in labs. From the hydrogen that fuels the sun to the calcium that makes your bones strong, these elements are everywhere. They are the essential components that combine in countless ways to create the incredible diversity of matter we see around us. They are the building blocks, and the next step is to see how they are all organized. With over 100 elements to keep track of, things could get very confusing. Luckily, a brilliant chemist named Dmitry Mendeleev came up with an amazing organizational chart called the periodic table. The periodic table is like a giant, detailed map of all the elements. It arranges them in a very specific way that helps us understand their properties and predict how they will behave. It's one of the most important tools in all of science. It puts every element in its proper place, telling us its secrets at a single glance. It's the ultimate cheat sheet for chemistry. The table organizes the elements by their atomic number, which is the number of protons in their nucleus. It starts with hydrogen, H, with 1 proton at the top left, and goes up one by one as you move across the rows. The rows are called periods. As you move across a period from left to right, the atoms get a little bit heavier and their properties change in a predictable pattern. All the elements in the same row have the same number of electron shells, which are the energy levels where the electrons hang out around the nucleus. The columns of the table are called groups. This is where the real magic happens. Elements in the same group behave in very similar ways. They are like families with shared characteristics. For example, the elements in the far right column, like helium, neon, and argon, are called the noble gases. They are very stable and don't like to react with other elements. They are the cool, aloof celebrities of the element world. The elements in the first column, like lithium and sodium, are the alkali metals. They are super reactive and love to connect with other elements. The periodic table is more than just a list. It's a story of relationships. By looking at an element's position, a chemist can guess if it will be a solid, liquid, or gas at room temperature, if it will be a metal or a nonmetal, and how it will react with other elements. The table even had gaps in it when Mendeleev first created it, and he correctly predicted the properties of elements that hadn't even been discovered yet. It's a powerful and elegant map that brings order to the chemical world, making it easier for us to explore and understand. So atoms are kind of like social creatures. Most of them really don't like to be alone. They actually prefer to team up with other atoms to become, well, more stable. When 2 or more atoms join together, they form what's called a molecule. A molecule is the smallest unit of a substance that still has all the properties of that substance. Think of it, like a team of players. Sure, an individual player has skills, but it's really the team working together that plays the game. Molecules are the teams of the chemical world, and the bonds that hold them together are the secret to their teamwork. Atoms connect with each other by sharing or trading their outermost electrons. These electrons, called valence electrons, are the ones involved in forming chemical bonds. One common type of bond is a covalent bond where atoms share electrons. A great example is a water molecule, which has the chemical formula H2O. This means 1 oxygen atom shares electrons with 2 hydrogen atoms. By sharing, all 3 atoms become more stable and, happy. They stick together like best friends, forming the amazing substance we know as water. Another way atoms can bond is by transferring electrons. This is called an ionic bond. It happens when one atom gives one or more of its electrons to another atom. When an atom loses an electron, it becomes positively charged. When an atom gains an electron, it becomes negatively charged. These charged atoms are called ions. Since opposites attract, the positive and negative ions are pulled towards each other, kind of like tiny magnets. A common example is table salt, sodium chloride, NaCl. A sodium atom gives an electron to a chlorine atom, forming a strong ionic bond. The way atoms combine to form molecules determines the properties of, well, everything around us. The structure of a molecule is incredibly important. For example, both diamond and the graphite in your pencil are made entirely of pure carbon atoms. The only difference is how the carbon atoms are connected. In a diamond, they form a super strong, rigid network, making it the hardest natural substance. In graphite, they're arranged in flat sheets that can slide over each other, which is why it's soft and can be used to write. The same atoms, arranged differently, create completely different materials. Now that we know about atoms and molecules, let's look at how they behave in large groups. All the stuff around us exists in different forms or states. The three most common states of matter are solid, liquid, and gas. What state something is in depends on how much energy its molecules have and how tightly they are packed together. It's all about how much the molecules are moving around. Think of it like people at a concert. Are they sitting still in their seats, milling about in a crowd, or jumping and dancing all over the place? In a solid, the molecules are packed very tightly together in a fixed pattern. They don't have much energy, so they just vibrate in place. They can't move around freely. This is why a solid, like an ice cube or a rock, has a definite shape and a definite volume. It holds its form. The molecules are like soldiers standing in perfect formation, holding their positions rigidly. They are locked into a crystal lattice structure, which gives solids their strength and stability. They are the most orderly and disciplined state of matter. In a liquid, the molecules have more energy. They are still close together, but they are not locked in place. They can slide past one another, flowing and tumbling around. This is why a liquid, like water or honey, has a definite volume but does not have a definite shape. It will take the shape of whatever container you pour it into. The molecules in a liquid are like people in a crowded room, able to move around and mingle but still staying pretty close to each other. They have enough freedom to flow but not enough to escape completely. In a gas, the molecules have a huge amount of energy. They are spread far apart and zip around at high speeds in all directions. A gas, like the air we breathe or the steam from a kettle, has no definite shape and no definite volume. It will expand to fill any container it is in, no matter how big. The molecules in a gas are like a few dancers in a massive empty ballroom, flying from one corner to another. They are wild and free, barely interacting with each other at all. Adding or removing energy, usually in the form of heat, is what causes matter to change from one state to another. Chemistry gets really exciting when things start to change. A chemical reaction is a process that transforms one set of chemical substances into another. It's like taking your Lego bricks, breaking apart what you've built, and using the same bricks to build something completely new. In a chemical reaction, the atoms in the starting substances, called reactants, rearrange themselves to form new substances, called products. The atoms themselves are not created or destroyed, they just find new partners to bond with. It's the ultimate remix. You see chemical reactions happening everywhere, every day. Cooking is full of them. When you bake a cake, you mix together flour, sugar, eggs, and baking soda, the reactants. When you put it in the hot oven, a series of chemical reactions takes place. The baking soda reacts to produce carbon dioxide gas, which makes the cake rise. The heat causes other reactions that change the color, flavor, and texture. The final cake, the product, is completely different from the gooey batter you started with. You can't just unbake a cake. The change is permanent. Another common example is rust. If you leave an iron object like a bicycle or a nail out in the rain, it will eventually start to rust. This is a slow chemical reaction. The iron from the nail reacts with the oxygen from the air and water. This reaction creates a new substance called iron oxide, which is the reddish-brown, flaky stuff we call rust. The strong, shiny iron has been transformed into a weak, crumbly product. This is a type of reaction called oxidation, and it shows how elements can change their properties when they react. Chemical reactions can release energy or absorb it. A reaction that releases energy, often as heat and light, is called an exothermic reaction. A burning campfire is a great example. Wood and oxygen react to produce ash, smoke, and carbon dioxide, while releasing a lot of heat and light that keeps you warm. A reaction that absorbs energy from its surroundings is called an endothermic reaction. An instant cold pack is a good example. When you break the inner pouch, chemicals mix and absorb heat from the outside, making the pack feel very cold. These energy changes are a key part of what makes chemistry so dynamic. Let's meet another fascinating pair of chemical characters, acids and bases. You've probably heard of them before. They are two special types of chemicals that are basically opposites of each other. Scientists use something called the pH scale to measure how acidic or basic a substance is. The scale goes from 0 to 14. A pH of 7, right in the middle, is neutral. Pure water is a perfect example of a neutral substance. Anything with a pH below 7 is an acid, and anything with a pH above 7 is a base, also called an alkali. Acids are substances that often taste sour, though you should never taste unknown chemicals. They are good at dissolving things. You can find many acids in your daily life. The lemon juice you put on your food contains citric acid. The vinegar in your salad dressing contains acetic acid. Your own stomach produces a very strong acid, hydrochloric acid, which helps you digest your food and kill harmful bacteria. Strong acids can be very corrosive and dangerous, but weaker acids are common and useful in many foods and cleaning products. They are the zesty, sharp members of the chemical world. Bases are the opposites of acids. They often feel slippery to the touch and can have a bitter taste. Common bases include baking soda, which you might use in cooking or cleaning. Soaps and detergents are also basic, which is what helps them cut through grease and dirt. Strong bases can be just as dangerous as strong acids and can cause serious burns. They are the smooth operators of chemistry, working to neutralize their acidic rivals and clean up messes. They are essential for making everything from paper to drain cleaner. When an acid and a base are mixed together, they react in a process called neutralization. They cancel each other out, producing two neutral substances, water and a type of chemical called a salt. For example, if you mix hydrochloric acid, a strong acid, with sodium hydroxide, a strong base, you get neutral water and sodium chloride, which is just plain old table salt. This reaction is incredibly useful. Farmers use bases like lime to neutralize acidic soil, and you might take an antacid tablet, which is a base, to neutralize excess acid in your stomach and relieve heartburn. As we've seen, chemistry isn't just something that happens in a laboratory with bubbling beakers and scientists in white coats. It is happening all around us, every second of every day. It's in the food we eat, the clothes we wear, the air we breathe, and the technology we use. From the complex reactions that power our bodies to the simple act of striking a match, chemistry is the science that explains how our world is built and how it works. Understanding its basic principles gives us the power to understand and shape our environment in amazing ways. The importance of chemistry goes far beyond just understanding the world. It is a powerful tool for solving some of the biggest problems facing humanity. Chemists are at the forefront of developing new medicines to fight diseases. They design and create complex molecules that can target viruses, kill cancer cells, or relieve pain. The development of antibiotics, vaccines, and countless other life-saving drugs is a triumph of chemistry. Without the ability to understand and manipulate molecules, modern medicine simply would not exist. It's a field that directly improves and saves lives. Chemistry also plays a vital role in protecting our planet. As we face challenges like pollution and climate change, chemists are working on solutions. They are developing cleaner ways to produce energy, such as more efficient solar panels and better batteries for storing power. They are creating new methods for water purification, designing systems that can remove harmful contaminants and provide safe drinking water to communities around the globe. They are also inventing biodegradable plastics and new ways to recycle materials, helping us reduce waste and build a more sustainable future. From creating stronger, lighter materials for building airplanes and cars, to developing the fertilizers that help feed a growing world population, the applications of chemistry are endless. It is a creative, dynamic, and essential science. By learning about atoms, molecules, and reactions, you are learning the language of the universe. This knowledge opens up a world of possibilities and helps us appreciate the intricate beauty of the world around us. Chemistry is not just a subject in a textbook. It is the key to innovation, progress, and a better future for everyone.